All right, I will try to Yale. Let's see, next week we do not have a colloquium, but instead we'll have the Sacred lecture given by the Nobel laureate Professor Takaaki Kashida. He is going to talk about the neutrino oscillation at the super K. Today, our colloquium speaker is Professor Angela Olinto. She got her PhD from MIT, and then she spent some time at Fermilab as a postdoctoral fellow. And then after that, then she moved to Chicago for all the years, and now she is the chair of the Department of Astronomy and Astrophysics, even though she told me her term will be up by the end of the month. But so it's very impressive that she is leading one of the important institutions in this country for such a long time. Professor Olinto has played a very important role in several very important astrophysics physical projects. She is the principal investigator of usual SPN, and also Poema, and also so-called JEM, the usual. She also is a key member of one of the largest surface array for cosmic ray study called Pierre Auger. She also very active in say the national and also international community, playing a very important role in many decision making. She also has a number of honors and awards. For instance, she is the fellow of the American Association of the Advancement of Science and also the American Physical Society. Today, she is going to tell us about the extreme energy cosmic frontier. So let's welcome Professor Olinto.
Thank you. Now it works. So thanks again. It's wonderful to be back here, and it's lovely to be able to have time to talk to you about what I've been up to these days. But it's not just me. There's lots of people involved in this work. And throughout this talk, I will mention the Auger Observatory, which has 500 collaborators plus, and some of the work that we've been doing most recently, which is this balloon payload, USPB-1, and a design for a space mission called Poema, and many collaborators, some even in this up the hill from here, Eleanor, who can't be here today. But the story that I'm going to tell you about starts about a little bit over 100 years ago with another balloon. So ballooning seems to be the way to go with cosmic rays. And this balloon was what established in 1912 with Victor Hess taking care of these detectors. He basically showed that the ionizing radiation that we now call cosmic rays come from outside the Earth and not from the Earth itself. And this is just going in altitude on the balloon up to almost 6 kilometers, 5 kilometers, and looking at the rate of these ion pairs, and they are going up and up and up. So this shows that cosmic rays are coming from outside the Earth. That at that time was not clear. And since then, we've been trying to understand the origin of these cosmic rays. A little bit later in 1937, Pierre Auger showed that these cosmic rays not only come one by one, hitting the top of the atmosphere, but from time to time they have so much energy that they generate what's called an extensive air shower. So one subatomic particle hits a particle, some atom in the atmosphere, and that interaction is so powerful that it generates hundreds of billions of particles into this long shower that hits the ground. And he showed that by basically putting detectors at different distances and seeing that they were being hit by particles at the same time. And that would be very difficult to do randomly, that they really needed to know that they were produced at the same time. And he estimated back in 1937 that the energy of these particles were about 10 to the 15 electron volts, which is really energetic. And then in the early 60s, in 62, John Lindsley showed that these particles that do these extensive air showers, they reach energies of 10 to the 20 electron volts, which is really an unbelievable amount of energy. Very hard to explain astrophysically how to produce these particles. So let me show you in a sort of scale to place you what types of energies and why do we think this is really energetic. So this is the way we explain the view of the universe that astronomers have. They use telescopes in the radio waves all the way to gamma rays, and this range is how we use, so this different frequencies, different energy range is what we use to explain what we see out there. If you include cosmic rays and even gamma rays and neutrinos, basically the number of orders of magnitude is basically doubled. So we have twice as much orders of magnitude in cosmic rays, and I'm showing this as pianos up here just to give you a sense of how many pianos you need to cover this range. And basically we have twice as many orders of magnitude in energy in cosmic rays as we have in the sort of typical astronomers' multi-wavelength universe. And recently we all have enjoyed the news about gravitational waves, that we have again, another order of magnitude going this direction, so larger and larger wavelengths or slower and slower frequencies. And I should turn this off because they're a pretty song, but not that wonderful. So anyway, so this is the kind of, we are here in the gravitational wave world, and in principle, Lisa and the pulsar timing will bring it even further. So there's really a lot of different frequencies or different energy ranges that we can use to describe the universe, and each of them tell us different stories. And so what I'm going to spend most time on is on the cosmic rays, but just to give you a placement. So here is the spectrum of cosmic rays, simplified and tried to show everything in one plot. So you can see that the cosmic ray spectrum, this is the energy squared times the flux. And this, you have the proton domination. So protons are dominating at low energies. And then in the cosmic ray, in the nuclei, you actually have a transition from protons to heavier nuclei when you get to what we call the knee area. And these are different data from different experiments, because we're basically having 12 orders of magnitude in energy, but 30 orders of magnitude in flux. So you can't do that with one experiment. And then under dominant, you have electrons, positrons, antiprotons. These all are part of the cosmic ray spectrum, as well as gamma rays, if you wish. But these are all under dominant compared to the nuclei, which are really dominant. And here in the bottom is what the interaction energies would be for the Tevatron, the LHC, Hera, and Rick, to give you a sense of comparison with what we can do in the laboratory. But we certainly cannot do the types of energies that we're talking about, the highest energies. So let me give you a guidance by just simplifying again the cosmic ray spectrum. It looks very featureless that way, so it looks like a power law, a very steep power law. That actually hides that there are different ranges in here. So when you see this turnaround at low energies, this is really the solar influence. So the fact that we are in the solar system with a magnetic field makes the effects of the cosmic rays that can be galactic around the sun, around where we are in the solar system, different. So this is solar influence region. As you go up in energy, it becomes galactic cosmic rays. So the sun doesn't really turn these guys around anymore because they're too energetic. And eventually, as you go to the highest energies, we expect these to be extragalactic cosmic rays. But the evidence for this was not really at hand. It was basically, we expected it given the energy scales and the magnetic fields of the galaxy. But now we know for sure that these things are extragalactic and when they begin. And I'll show you that in a second. This is a mixture in the simplification of many different types of experiments. There are space experiments for the low energy cosmic rays and then ground experiments for the very highest energies. So here's, for example, a list of space experiments that are ongoing, which are trying to understand the in situ cosmic ray flux. And one of the best places to do cosmic ray science these days is the International Space Station, which has the AMS, which is over here in this range, but this is a very large experiment to basically detect particles with many different detectors, and that you also looking for indirect dark matter type things. CALET, which joined the JAM, the Japanese experiment module over here in 2015, and Ice Cream that just went in August 20. Ice Cream is ISS Cream, which was launched in August 2017 and is now on the JAM also. So these are 3 examples of experiments covering the low energy cosmic rays, and these are operating now and doing brilliant measurements to try to extend the low energy detections of all different kinds of nuclei all the way to the very highest energies, but also positrons, electrons, antiprotons, which is where the indirect detection of dark matter is being studied. So you also have free flyers like Pamela Dampe Nucleon, which are also doing this kinds of low energy cosmic rays. In terms of cosmic rays as opposed to indirect detection of dark matter, the interesting results at low energies is that the spectra of proton, helium, lithium, they do not seem to follow the exact same power laws. So there is this sort of low energy change due to the solar influence, but eventually we expect it to be a power law, and we expected protons in helium and lithium to have all the same power laws, and they don't. So this is an interesting discussion. What is generating all these different types of elements and their power laws. So when I show this type of plot, it looks very calm and nitty and well organized. But when you put all the data we have with the composition, it looks very turbulent. This is the kinds of models people are talking about, trying to fit the data in the different energy ranges. So things are going up and down. It's pretty complex for this overall quiet-looking thing at the end. So this is very active at the low energies and also at the highest energies, and bridging the two has always been a challenge because this is space detection and this is indirect ground detection, and I'll talk more about that. So let's go to the ground. The ground experiments are what we use over here, and what I'm trying to do eventually is to be able to open a window to space at the highest energies. But let's talk about what we can do right now. So here's the data from ground experiments that you can see at the highest energies, and this is now the flux multiplied by e to the 2.5, and now you can see a little bit better the knee change over here and the ankle and the turnaround. So these are three features that and there's maybe some bumpy area over here too, but these are pretty obvious features that you can see when you multiply by this power, for example, when you take this sort of closer look. And here, again, are the kinds of interactions that we have at the LHC. And this is the kind of center of mass interactions for protons, PP, that we're observing at for these kinds of particles. So in terms of particle physics, we're really detecting much higher, and this guy hopefully won't die on us. And you can go orders of magnitude above what we can test in the laboratory, which is wonderful because we can, in principle, discover new things. It's also difficult because it's hard to interpret sometimes what the cross-sections and what the development of these particles in the atmosphere looks like. So this is, again, just to show that we can reach about 500 TeV at 10 to the 20. For the low-energy cosmic rays, we seem to have a very good story to tell with some evidence, but not completely solidified yet. But that for the low energies, it seems like a supernova remnants with their shocks is sort of the best candidates for explaining galactic cosmic rays. We have some evidence from gamma rays that show that there is really some acceleration sites around supernova remnants, but it certainly cannot be expanded all the way to the highest energy. So by the knee time, basically the energy for galactic supernovae cannot explain past the knee very well. With protons, and then you have a whole cascade of different elements. So we have two questions. One is what's doing the extragalactic cosmic rays, and the other is where the transition happens between galactic cosmic rays and extragalactic cosmic rays. And I'm going to focus most of my attention to the ultra-high energy cosmic rays, which by definition is above 10 to the 18 electron volts, which we also call an EeV. So I will tell EeV and 10 to the 18 different times. So these are what we call ultra-high energy cosmic rays. And to accelerate something to the energies we're talking about, let's think of our favorite accelerator, the Large Hadron Collider. The Large Hadron Collider has 27 kilometers and about 10 Tesla magnets and reaches 14 TeV. Now, if you wanted to put, instead of 14 TeV here, 10 to the 20 electron volts, then you would have, with the same magnets, a ring which would be the size of the orbit of Mars around the sun, which is a Mercury, not Mars, sorry, a Mercury orbit around the sun. So that's way too big for any Department of Energy type funding. So you definitely need to pump up the magnets if you want to do it in 27 kilometers, right? So what I'm doing here is either changing the magnets, making it stronger so I can bend the particles more, or I'm making the circle much, much bigger with the same magnets. And what this means is a translation of what we call the Hillis plot. So before you try to figure out which accelerator in the universe could reach 10 to the 20, you do want a plot like this just to basically rule out most things, most options. So for example, here's the sun, here's the earth, this is the LHC over here. And what am I plotting? I'm plotting magnetic fields versus sizes, the scale, so the ring size. So the LHC ring versus its magnet. The Earth magnet and the size, the radius of the Earth, and the same thing with the sun. So these are not going to they're not going to contain protons of 10 to the 20. The blue line is the requirement that the magnetic field and the size, the scale of your ring, contains a 10 to the 20 electron volt proton. In red is the same requirement for iron. Iron is more charged, so it's easier to contain iron versus proton. So you gain a factor of Z, and it makes it a little less stringent. So if you're going to be accelerating iron for 10 to the 20, it's going to be a little easier than accelerating proton at 10 to the 20. So once you put these lines and you put the scales correctly, and you just drop every single object you know in the universe over here, what you find is that there are no objects on this side of the plot. There's nothing we know that would go here. And this would be the best favorite candidates. If there was anything on this side, then that means that you would have some type of event or object in the universe that can contain protons above 10 to the 20, and then you can make your accelerator less efficient and lose some energy and go to 10 to the 20. But right now, what we have is a few candidates that barely reach the proton line, and those are neutron stars, which do go a little bit above, active galactic nuclei, which can have jets, hotspots, or just the nucleus itself, and they all fit in that line. There's some scaling here. And gamma ray bursts that also move as a function of time, so they, again, have different scales. Supernova remnants, for example, don't quite make it, and intergalactic shocks, in very, very large scales, intercluster shocks and such, they are pretty large, but as far as we can tell, they cannot really do the job. So in terms of possible candidates, we really end up with neutron stars and AGN and gamma ray bursts. For example, these are two such models. This is a whole effort over here. This is an actual calculation of a little bit of acceleration of ions in a neutron star. But what we're talking about is to actually reach 10 to the 20, we would need very, very fast spinning newborn pulsars to do the job. And it's doable, but it's like the very special ones. So it's almost like gamma ray bursts in terms of the number densities of them. There's also this express acceleration model, which is quite nice, which is an AGN jet basically re-accelerating the galactic cosmic rays with a gamma squared type one hit acceleration. So that also seems to do a good job. Okay, so this is so far just an idea of what possibly could do this, but none of these have been proven to work 100%, and we still would like to see an actual smoking gun, either pointing to some objects in the sky, for example, or really knowing exactly what the neutrino spectrum of these things look like and measuring them to decide if it's going to be something very compact or something very, very large, like a very massive black hole. So what we do instead is we also keep doing different models, but measuring better and better this at the highest energies in particular are going to do the job for us, as I'll show you in a second. Now the challenge to measure these particles is that the flux at the knee is 1 per meter square per year, so you can imagine doing something, even putting something of meters square in the sky, up above in space. But over here is 0.1 per kilometer square per century. So the flux is so low that either you have a lot of patience, because you're going to if you had a kilometer square detector, it would take a century to see one of these showers. So it's very challenging. So how do we measure these things? How can you measure something which is less than a tenth of an event per kilometer square per century? So the way we do this is we use the atmosphere. So the good news is, as I showed before, and the thing that Pierre Auger discovered, is that one particle will multiply into so many that you can actually see this shower development if you have a very fast camera, for example, in the UV, or if you put detectors on the ground. So what you're seeing here is following the center of mass of a particle interaction in the atmosphere. This is a proton at 10 to the 14, just to give you a sense. And the different colors are the different particles. You have hadrons in blue, muons gray, neutrons in green, and electromagnetic in red. And you see a lot of electromagnetic particles which basically trace this altitude development here. So this is the shower development. It peaks and then it dies off. So, and this is in kilometers, so you have 20 kilometers up, you start the interaction, it reaches a peak and dies off. And these electromagnetic emission, that the particles that are doing this shower, you can actually see because they will interact with nitrogen in the atmosphere and they will cause fluorescence of nitrogen. So by looking at nitrogen fluorescence, you can actually see the shower development. Another way to detect it, so one is to look at the development in the atmosphere. The other is to place detectors on the ground. And here's what the distribution of electromagnetic and muon signals and others in neutrons and such at different distances from the core. So for this energy, you would place detectors at 200, 400, 600, 800 a kilometer and such, 1,000 meters. And then you can do the whole distribution of that cascade. So that's the two ways of trying to detect these particles. And the two leading observatories at the highest energies use both techniques. So here is the two leading observatories of ultra-high energy cosmic rays. In the northern hemisphere, we have the telescope array in Utah, which is a 5-country collaboration. It's an area of 700 square kilometers, and it has 3 fluorescence telescopes overlooking that area, that array. At the Pierre Auger Observatory, which I'm involved in, is in Mendoza, Argentina. We have 19-country collaboration, and we built the largest array ever, 3,000 square kilometers, with 4 fluorescence telescopes overlooking the site. This feat of doing this humongous detector was thanks to many people, but in the leadership of James Cronin. Jim Cronin passed away last year. He was the leader at Chicago that got a lot of us involved in this. And here's the video of what it would involve. So you have some source in the sky that sends some particle at the very highest energies. That particle interacts, makes the cascade. You have detectors on the ground that detect the particles directly. And then these blue lines are basically the inverse of what should happen, which is light from the ultraviolet fluorescence goes to your telescopes as opposed to this other direction. So outreach sometimes gets the direction wrong. And we have more than 500 scientists and 19 countries in this collaboration. So here is what one actual event looked like before we finished the array. And this is one event that has both the ground and all the 4 fluorescence telescopes observing it. This is our display. And now you can actually see what our detectors look like. They're very self-sufficient units, a tank of water with photomultiplier tubes looking for the shrink of light produced as the particles cross it. This is the Andes in the background. This is a very large flat area just next to the Andes in the Argentinian Pampas, Pampas Amarillas. And you have basically a self-sufficient detector, so you have to have solar panel, which you can't see quite here, and a radio communication to the central station. And here is the distance between them is 1.5 kilometers. So you see one tank here, the next over there, the next over there, and a whole array of these things, 1,660 of these spread into the Pampas. And then we have these 4 telescope stations, 4 fluorescence telescope stations overlooking the site with 30-degree opening angle in the vertical, and then 180 degrees the other direction. Here's what these things look like on the inside. So this is the top of one of these telescopes, and you have basically 6 telescopes looking out, observing the fluorescence light. Inside the room, this is the scale of the camera and me. The camera is over here. You get the light at night. You get the light through this opening with some mirrors that correct which help your field of view. You have a spherical mirror and then photomultiplier tubes as your camera, as opposed to having CCDs like what you have in your iPhone. And the reason for PMTs is because the signal is moving at the speed of light, so it's really fast. So it wouldn't have, the camera in your phone would not react fast enough to collect all that light. So we need to use something faster. So that's the Pierre Auger Observatory. So this is what it looks like when it's finished. It has these 1.5 kilometer array with 1,600 detectors. Then there's 60 detectors that are a little bit more packed around here. And we also have extra telescopes that have been deployed. And right now we're deploying something called Auger Prime, which is an extra detector on top of each tank to separate the muons from the electromagnetic particles going through the tank. The reason for this is because we see way too many muons in the showers and we don't understand why. So this upgrade of trying to separate the electromagnetic from the muon is important to understand the interactions of these particles. So here's one of the products of this effort, is a very nice measurement of the spectrum. So we actually have a precision type measurement of the spectrum, which in this business is quite a challenge. And here again, it's E cubed times the flux. So this is very, very steeply falling cubed energy trend. So this is even faster than you can imagine. And these numbers are the number of events per bin. And you see that we run out of statistics around 19.5. But before 19.5, we see very nicely the change from one type of probably galactic, maybe not. There's discussion if this is galactic or not. But this is certainly extragalactic coming in and turning around. Now, when you see this turnaround, you would expect it to be for one reason. But then we are now very confused. And I'll explain the turnaround soon. Let me just tell you about the telescope array, which is in Utah. It's of these countries, 5-country collaboration. It's 3 fluorescence stations that are shown here, and 507 scintillator detectors, a little bit different than the water tanks, but they do the same type of thing, where they have the hybrid detection of the particles hitting the detectors on the ground and the fluorescence. And here is a double-decker, which is this telescope here, and you see one of these events, which is this light little blip moving very fast. So this is moving, say 40 kilometers away at the speed of light, and this is what your camera records. So it's a video camera that's moving very fast. The spectrum for the telescope array, once you correct for 10% off energy offset, it fits very nicely with the Auger one, except for the highest energies, but it's within the statistical error bars, because the telescope array has less statistics than Auger, but that does look like there's more stuff happening in the northern hemisphere than in the southern hemisphere. And since I am from the southern hemisphere, I think that's very unfair. Even in the sky, there seems to be more cosmic rays in the northern hemisphere than in the southern hemisphere. Go explain that, right? Here is actually the coverage. So here you're seeing the exposure of Auger in black, and the exposure of the telescope array in green. And this is the overlapping region. And when you look at the spectrum in the overlap region, you actually see the same spectrum. But then you can see that there is a declination dependence not in the telescope array, but not in Auger. So maybe there is a source in the north which is creating that difference at the highest energies. So what is this turnaround? So I mentioned something called GZK. So this is something that this field was looking for. And it's called the Greisen-Zatsep-Kuzmin cutoff. So this is where GZK come from. And these 3 gentlemen, one in the US, 2 in the Soviet Union, proposed it in the 60s as soon as the microwave background was detected. So the microwave background, which is shown here in its fluctuations, is a background which interacts with any proton. So if you have a proton of high energy traveling through the universe, it will interact with the microwave background, which is everywhere. It will make delta resonances and produce pions in that background. So the proton that you start with will be transformed into a lower energy proton, lower energy than 10 to the 20. So it will lose some energy by pion production. And this basically gives a horizon to the kind of protons we can see at highest energy. So these gentlemen predicted that there would be a horizon of protons that above 5 times 10 to the 19 or so, you wouldn't see any more protons. They also mentioned that for iron, it would be photodissociated. So even for higher nuclei, you photodissociate them. And this is the same effect, but shown here as a function of the distance. So this redshift is a way to tell the distance between us and some object. So if you have a source at 0.003 redshift, so very nearby, then the spectrum that you have from that source will not be modified up to 10 to the 20, and then you will have a little bump of the particles that above 10 to the 20 lost energy and now are 10 to the 20. As you move to higher and higher redshift, the microwave background becomes hotter and hotter, so you end up moving this peak to lower and lower energies, and the overall spectrum will have this shape. And this is what we could be measuring if we are looking at the highest energy cosmic rays, the GZK effect. So to summarize in terms of the spectrum, the Auger and telescope array agree on the shape of the spectrum. We see an ankle and we see a GZK-like feature. The differences at the highest energies are consistent within the errors, but maybe there is more flux on the north. Maybe there is a nearby source on the north. We don't know yet. But we don't see any recovery, so we don't see any evidence of a very nearby source, and we do not need any physics beyond the standard model to explain what's going on so far. So let's ask the following questions. Can we know what the composition of these very high energy particles are? Are they all protons or not? What are the anisotropies in the sky? Do we have any pointing? Do we have any sources? And then do we have any multi-messengers? And by that I mean photons and neutrinos that could help us figure out what are the sources of these particles. So how do we do composition? So remember our little video of what a particle shower would look like if you were sitting with the center of mass of that particle. So if you're in the telescope, what you see is an increase in light and then a decay. So this is what we call a sort of longitudinal distribution of the shower, and there's a peak. That peak in grammage per centimeter square is the depth of shower maximum. So there is a depth of shower maximum given for a given energy and a given composition. So here in this slide, you can see the depth of shower maximum, or the depth of the shower, sorry, as a function of the number of, and here's the number of electrons, or electromagnetic production, which is what this plot is about, for different elements. So if you have a gamma ray, the gamma ray shower will tend to develop much deeper in the atmosphere, so you won't even see the peak. While if you are talking about a proton, this would be the blue development, so it's deep, but not as deep as gamma rays. So you would have a peak and then a decay, and this is the Auger altitude. But if you input iron, again, you will have a peak, but even higher altitude than protons. So if you're looking at the maximum of the shower, and it's higher, then it should be iron. If it's lower, it should be protons for a given energy. Now, there's another feature that you can compare, not just the peak of this distribution, but also the width of the distribution. So in blue, you have the variation for a proton shower. It's much wider than the variation for an iron shower. Okay? So we can use two measurements. One is the average X max, as we call it. X max is the maximum of the shower, the depth of the shower maximum for a given shower. And here is what the proton simulations would look like in red, and the iron simulations in blue, and our data in Auger in the middle here. So it tends to go to protons and change its mind and then go to iron. You also can look at the fluctuations of, so here's that same plot. So this is the average of the peak of the shower for protons, for iron in the data, that shows a change in composition going to protons and then turning around and going to iron. And anything between iron and proton are lines in between. And here's the fluctuation about the mean. And so if you have high fluctuation, it should be protons in red. And if you have less fluctuation, so if they all look the same, it should be iron. And again, you see the same trend, which is kind of proton-rich going towards iron. If you translate these data into log of A, so you actually can see the actual elements, and proton would be here, helium, nitrogen, and iron. You see the data sort of going towards proton and changing its mind. Now I don't have just one panel of this kind of translation. I have three, one for EPOS LHC, one for QGIS Jet 4, and one for Sybil. Those three names are different hadronic interaction models, and they give you different results. The shape of the data is the same, so the data has this V shape, meaning changing towards light and then going towards heavy. But if you really want to know if light is proton or helium, you need to know how to translate that through the interactions. And as you can see, these three packages, they should basically predict the same thing, and they don't. So it's very difficult to be independent of hadronic models when you try to actually label each of these pieces as a different element. And this becomes even messier in this plot, which I keep saying it looks more like a music sheet than an actual data translation, but because we have those three same translators, so QGIS Jet, Hadronic Interaction Models, EPOS LHC, and Sybil. EPOS LHC was our favorite because it's been tuned at the LHC, but it's an interesting, it gives you even fewer muons than you expect. So we have a little issues with that. And here you have the proton line, the helium line, the nitrogen line, and the iron line. And you see that basically, we are consistent with not seeing much iron until the end or in the beginning. And nitrogen also seems to want to pile up around here. Helium takes over a little earlier, and proton peaks and dies. So at the highest energies, at around 10^19.5, we don't have many protons around. So that has changed the whole GZK interpretation. So the fact that all the elements are changing just when the thing is turning around has another explanation. So the cooler explanation was, interaction with the microwave background. But maybe it's just the maximum energy of the actual accelerators, and we can't tell those two apart. So here is the spectrum, and here is the idea that you have a GZK cutoff in black. So this is just the effect of a propagation through the microwave background, turning your flux around at 10 to the 20. And here's another as good model, which has the composition that we're talking about. Protons coming up and down, helium in the bottom here, CNO, and then iron. So by changing the elements, by looking at the composition, then the fact that we have this turnaround may be due to the maximum energy of the accelerator and not necessarily anything to do with the propagation from the source to us, which to us was a big surprise. Another big surprise is what I mentioned, that there are way too many muons. Here is the maximum of the muon shower, which is a specific way of looking at the muon production depth. And this is where the data is, and the range, so this is iron in blue. So if you picked Apos, for example, which would be the dashed line, then we're heavier than iron. So I was joking that we're only seeing the gold that came from the two neutron stars. So this is all gold coming from extragalactic sources, so it's much heavier than iron. But for QGS jet, it's still on the iron line, so it's not completely ruled out, but it's a bit surprising, which is why we're doing this Auger prime, putting these detectors on top of the tanks to be able to separate the two things. At the same time, the telescope array is building 4 times its size, so it's going to match in size Auger. So we're going to have in the north and in the south the same coverage of these effects. Okay? So we will, in the future, have a lot more data coming from the north, and the idea that the flux in the north is stronger will be verified. And what about anisotropies? This is where things get really fun, because if we're going to see sources, it will be through anisotropies. So unfortunately, at direct peaks of, so this is 2 maps of the sky, the telescope array map and the Auger map, and we basically have 2 3 sigma overdensities in the ray. So we have some hints of having sources in these 2 hemispheres, but they're really at the 3 sigma level. And we cannot really publish this as being the first detection of sources, but at least there are hints. Now, the catch on the hints is that they occur above 60 eV, which is not surprising. You would expect pointing to happen at the highest energies, because lower energy cosmic rays will be bent around by magnetic fields. So you need to be at the very highest energies to be able to point. So here is, just to follow what's called the telescope array, or the TA hotspot, which seems to be evolving year 5, 7, and 9. But they basically have pre-trial 5 sigma type things. But if you do the actual penalties, it's all around 3 sigma. Now, the most exciting recent news in this business is the dipole. So here is what we expected. So these are limits of dipoles. So if you do a dipole study, if you look at the sky and you say, is there a dipole component of my distribution? Then people would put limits on those dipoles. So this is cascade and run, and this is a function of energy. So this would be the equatorial dipole amplitude. And Auger had limits also. There should be a dipole due to the fact that we're moving with respect to the background of extragalactic cosmic rays, and this would be at this level over here, but we're not there yet, and we did see a dipole earlier. So the dipole level is up here, which is pretty high, and that's very exciting. So let's look at this dipole. First, let me tell you what the exposure looks like. So this is the exposure maps in equatorial and galactic coordinates. Now, if this dipole is pointing towards the galactic center, so this would be the galaxy is in this plane here, then there could be a way, we would have to be forced to explain a galactic component of these extreme energy cosmic rays. But it was not to be. So it's not going to be a galactic dipole. This is what the dipole looks like. So we did first a harmonic study in right ascension. So as a function of right ascension, what the different bins, just by doing declination additions, and you see this basically modulation. And then this is the actual map of the dipole, which is a 5.2 sigma post-trial signal. So after the penalizing for 2 bins of energy. So we did 1 bin which is above 8 eV, and another bin which is between 4 and 8 eV. So the number of events in the first bin from 4 to 8 is 81,000. And it's above 8 is 32,000. And the significance, the probability is 10 to the minus 6, this 5 sigma, above 5 sigma then. So here's what the dipole of Auger looks like in 3 different coordinate systems. Okay, so there's a dipole. That's really nice. Here's the galactic coordinates, and if the dipole was pointing in this direction, we would say maybe there is a galactic component to these extreme energy cosmic rays, which would basically throw all the models out the window. But, so the models stay where they are. So it's much more consistent with our prejudice, which is that this should be extragalactic cosmic rays. So it confirms our idea that these are really extragalactic, not pointing in this direction. But then where is it pointing towards? This is the pointing of the dipole. And if you ask, what is the large-scale structure around us, where would that dipole look like? It would be pointing here. So this is the 2MRS dipole. And I realize not everybody in this room is astronomer, so you don't know what 2MRS is. So I'll show you in a second what it is. But let me tell you that this is one measurement of the large-scale structure around us. And the thing about that point is that that doesn't equal that point, right? So there is some deviation here. But if you consider the magnetic field of the galaxy, the tendency is to move in that direction. So for a 5 eV and a 2 eV particle, that would be the direction that it moves. But even more interesting, in my opinion, is this plot, which is the supergalactic plane coordinates. And it looks like it aligns very nicely with that. So now there are many papers that are starting to come out trying to explain the dipole direction. I haven't been convinced by any of them, so I'm not going to get into any of them right now. But this is, the good news is that this is not galactic source, and there is a dipole, and it's not crazily far from the 2MRS. And that I mentioned already. So the 2MRS is the redshift survey part of the 2 micron all-sky survey, the 2 mass survey. So here's a picture of that 2 micron survey, which has a piece of it which is a redshift survey that I'll show you in a second in different redshift bins. And I don't know if you can see with this line, but there is sort of an extra amount of galaxies. These are all galaxies, each of these dots. And these colors are different redshift bins. So here's the redshift bins of different colors. It's hard to see with the light. But anyway, from 0 to 0.002 and then all the way to above 0.06 in redshift. And each of these shells give you different distances of the galaxies around us. And when you put it all together, it looks like this, and this is our galaxy. Now, you can see this wall, maybe, which is the supergalactic plane. And that's the way to translate back to this plot in the bottom here. So this is the supergalactic plane, and that seems to be showing us something, but right now it's not super well understood. But this is really exciting. Here is the data in terms of, by comparison to, the 99% confidence level for CLs is all in here. So no other multiple seems to be obviously departing from just isotropy except for the dipole. So we have the dipole. We don't have anything else at this point. And we're trying to now go from 8 to lower energies by, taking smaller bins and looking at more data and parsing it. To see how does the dipole get to exist? How does it get created? Does it move in any other direction? To summarize so far, we have a nice spectrum. And we have this dipole that starts right here in that spectrum, so 8 eV. And from here on, we know for sure it's extragalactic. Maybe it's extragalactic further down, or maybe there's a component which is extragalactic and another one that's galactic. And it would be nice to know which one is which by doing this. Seeing this dipole disappear, moving towards lower energies. And then we have these hot spots at above 60 eV. So the thing that we would like to do is get a lot more data here, because this is where the sources will show up. So so just to repeat what I said, there's an Auger dipole above 8 eV, and then above 60 eV there's the hot spot, and maybe that will become more significant if we have higher statistics. And what about multi-messengers? So the GZK effect, which goes through this delta resonance, or just creates pions directly if you have higher energies than that, give you 2 types of messengers that come from the same process. One is gamma rays from the pi 0, and then neutrinos from the neutron and from the other pions. So the neutrinos and the photons created this way, which we can call it cosmogenic, GZK, or which should be really called BZ neutrinos, because Berezhinsky and Zatsepin were the first ones to calculate that. So these are all for the same beast, but with different names. those are very interesting for this field. So if we can detect neutrinos and gamma rays, we can really point, because the protons, the iron, and all these other guys are charged. Magnetic fields turn them around. They mess up our pointing ability. If neutrinos and gamma rays are seen, then we can really point to the sources directly. So this is a major hope that we can see both of these things. For photons, this is the limits on photons. So people have been searching for them, and basically so far we have no detection of photons. But we eventually expect to see something. But the problem with photons is that they interact with the radio background. So it's not so easy to get them to reach Earth. So this might be a major challenge. Neutrinos, on the other hand, this is really where we are all excited about. And so I'm going to spend the rest of this time, which I'm trying to wrap up soon, talking about neutrinos. So the next week's talk will be about atmospheric neutrinos, I think, right? So here is the cosmic neutrino spectrum. There's cosmological neutrinos, which are very hard to detect. Solar neutrinos, which already gave a Nobel Prize. Supernova gave another one. Atmospheric one, another one. So this is very exciting times for all these kinds of neutrinos. And then IceCube has detected the atmospheric, also the atmospheric, but the astrophysical neutrinos. So the pink line is starting to be exploited by IceCube. And what we're looking at is this cosmogenic ones, which are much higher energies, and they're much lower fluxes. So again, flux is the challenge. There are limits from many different experiments trying to reach those, but so far we haven't seen any. But again, this is 2 orders of magnitude. This is the flux of these neutrinos versus energy, and they're 2 orders of magnitude of uncertainty, and new experiments will start taking bites out of this story. So I'm going to rush a little bit by telling you that so far there's no detection, but what I'm working on right now is how to, in the future, guarantee detection of these things. So what we're designing is called POEMA, which is the probe of extreme multi-messenger astrophysics. The idea of POEMA is to have 2 satellites looking down and basically using the biggest, so if you remember Auger and TA, they're looking up, but they're really looking at the atmosphere. It's as if we had a very large cloud chamber that we are instrumenting around. So if you go to space, you can look down on a much wider volume, much bigger volume of the atmosphere at the same time. So this will improve our acceptance, which will solve the problem of the limited statistics at the highest energies for the cosmic rays, and the limited statistics for getting, or the limited sensitivity to getting the BZ neutrinos measured. So we have a collaboration, and one of our collaborators is Eleanor Judd, who is up the hill in the Space Science Laboratory. And this group is a group of scientists of different experiments, Auger, TA, GEM-USO, OWL, Telescope Array, Veritas, from all over this field. And what we're doing is basically designing the best mission with a budget of $1 billion tops, okay? Sounds like a lot of money, but very quickly you use it all up. So in 2002, there was one similar study called OWL for the orbiting wide-angle light collectors. And we also had another study in 2000, which became USO, Extreme Universe Space Observatory. And the version of USO that goes to the GEM, the Japanese experiment module, is called GEM-USO. So this is one collaboration, this is another collaboration. We put everybody together to do the best we can do for $1 billion. The idea from both experiments is to look at the fluorescence from above. So you have the atmosphere, you see the fluorescence, and you see the Cherenkov. There's one extra element that we added to this story, which is neutrinos that are upgoing tau neutrinos that produce a tau that decay, and then you observe with the telescopes looking at the limb of the Earth, you look at the Cherenkov light produced by these tau decays. Okay, so you're looking not only down to see the showers, but you're looking at the limb of the Earth for showers that are coming at you with 5 degrees. So I'm going to skip, by collaboration and all this fun stuff, we developed a really nice camera, very fast, ultra fast cameras with PMTs, with multi-anode PMTs, and we put that together, and we have a whole program of doing this kind of telescope on the ground, but also in balloons, and then in the space station, and hopefully POEMA in the future. So what we've done so far is we flew 2 balloons, one overnight balloon, which looked like that, the red one. And here is the path it took from Timmins in Canada all the way down to a lake. And we had this circling helicopter under the balloon. So the very lucky graduate student happened to be at night in a So if you're a graduate student, you don't know what to expect. This one was lucky. He ended up in this helicopter in the middle of the night shooting lasers under a balloon, not knowing exactly what was going on. But he did a really good job. So here's one of these laser shots. So first you're going to see basically a lead lighter, and then the artificial ultra-high cosmic ray produced by the laser. And this is what the telescope looked like. So 2 Fresnel lenses plus our camera. And this is what it looked like before it was taken to New Zealand for another book. So this is inside the telescope. I'm going to skip all this. This is the camera, and this is the size of the camera compared to us. So you have a sense, and this is us ready to launch the second balloon. This now was launched, prepared for a long duration flight, an ultra long duration flight with a super pressure balloon. And here's the beautiful launch. This guy was really excited when it all worked, so were we. And you probably heard about this very famous 2016 COSY flight, because that was led by Berkeley, which had 46 days. We didn't get that lucky. We got a leak after the 3rd day, and we only had 12 days, and it was not the kind of orbit you expect. You expected, what we are hoping to have, which is what NASA is hoping to do, is a balloon that stays at 110,000 feet straight. But after the leak, it kept going down and down, and we would have ballast dropped, and it would come back up again. So by doing this up and down, it basically changed levels of winds. The winds on top are very different from the winds on the bottom, so it sort of random walked itself into the Easter Island, where it ended up being decommissioned, let's put it that way. In 4 days, it would, yeah, so we have now a beautiful sculpture, silver sculpture in the bottom of the ocean that the fish are enjoying very nicely, next to Easter Island. In principle, in 4 days, we should have been over Chile and Argentina, where they could bring it down and we would recover, but we lost everything. This is the kind of winds that we're hoping to catch at the highest altitude, but at lower altitudes, that doesn't work. But because NASA felt guilty, they gave us a lot of money for the next balloon payload. So here's the next balloon payload. Instead of doing this looking down business, we're going to be looking at the limb, just like the neutrino business that I told you about for Poema. So we're basically designing 3 telescopes, 2 to look down at the limb and the other to look at the high altitude showers. And those will be a pathfinder for Poema. Here's what Poema looked like when it came out of the Goddard Space Flight Center in late August. Next week, I'll be back there again to do the mission design. So this is the instrument design. It's a very large mirror that gets folded into this launch stowed position. Now, it's a very large mirror, but it will be below $1 billion because it's not JWST. It's as big as JWST, but it has much less precision in its surface because it's not doing imaging. So don't worry, we'll make the budget. Here is what the focal surface looks like. So it's a very large focal surface with the same type of telescope, the same type of detector system that we use in the balloon, plus a new feature here in red, which is silicon PMs to detect the Cherenkov signal of the limb, which is for the neutrinos. So here's what we expect to do. The 2 satellites looking across from each other so that we have a common volume to do basically stereo vision for ultra-high energy cosmic rays, satellite 1 and 2 looking down. And then both satellites looking at the limb, which is the neutrino observing pattern. So to give you a sense what that would look like, in California, if we're looking down, it would be all, a big chunk of California. If you're looking at the limb, it would be from the East Coast to the West Coast. So basically, that's the kind of volume of air that we'll be looking at to look at the limb neutrinos. And basically what we're looking at is neutrinos upcoming with 5 degrees from the ground, making a shower towards us because the tau decays in the direction. So to conclude, if we do this kind of space mission, we could have an order of magnitude more sensitivity to cosmic rays. So this is as a function of time, the exposure, and the telescope array and Auger are now the dominant way to do it. And then if we go to space, we should be able to do more. And this is the kind of expectations for Poema, but we are still simulating. That's why I have dashed lines. And then there is another wonderful project with in China for radio detection that might be down here. And then more, this is generation 3, let's put it that way. And generation 2 will be ARA, and Ariana, which in the next few years should be starting to take a bite of this neutrino flux. So to summarize, we have great progress with these giant ground observatories, Auger and telescope array. We did very nice measurement of the spectrum. The composition is very surprising. And the Dipole is very exciting recent discovery with the extragalactic sources being sort of verified. And then the question is, what are the sources? We still don't have real hard evidence for any of them. And then, to conclude, we are hoping to have a program that we're developing with balloons, but also thinking in the future to do a space mission at the probe scale to look at both neutrinos and ultra-high energy cosmic rays from space. Thank you very much.
Questions?
Oh, sorry. It's a big room, yes. I should be on this side. If it's changing with direction. So the answer is yes and no. So I'm not going to try to find the slide, but it's very low statistics at the, at the cutoff itself. As you see, we have 14 events. But if you just look at the Auger and the telescope array spectrum, it's already quite different at the highest energies. But the error bars are huge. So if those error bars were shrunk, but the average points stayed the same, we would already see that there is a difference. Even within the telescope array itself, it seems to have a declination-dependent spectrum. So, the hotspot could be the first source, right? But we don't know yet because it's a stable signal.
And you claim that the change in composition we see at the upper end near the UHECR cutoff was due to potentially an intrinsic energy limit in the source?
A maximum energy, yeah.
I guess I'm wondering, can you rule out the fact that there's a fractional composition of, say, iron or heavy nuclei, a small amount, and what you're seeing is just a transition to those in the UHECR cutoff?
Not sure I
If you had a few percent iron or other heavy nuclei, and the protons would be attenuated by the UHECR cutoff,
right.
would you naturally expect a
Right, so but if you saw the plot I showed, which is hard to imagine you could catch all the details, the proton has to die much earlier than its JZK cutoff. So the iron and proton get killed at the same kind of distance. So if you translate it into distance, proton and iron come from similar distances. Helium comes from very nearby, and CNO intermediate between them. So the proton needs to die off to get out of the way, basically, because the fluctuations. But if protons have more fluctuations than iron, so for the fluctuations to be so narrow, proton has to be gone. And for proton to be gone that early, it can't be the GZK. It's mostly the maximum energy. You have to sort of artificially cut it off, otherwise it will keep moving, right? So that's why it's a bit surprising, because to explain the fluctuations in the X-max, in the maximum of the shower, we really need to go heavier than protons, and protons have to be cut before they would produce a lot of. So they still, it goes, we are assuming these things go to high redshift, right? So this is a population that's all over the place. So if it is all over the place, there will be, at very high energies, still interactions with the microwave background. So there's always some GZK effect, but the main drive is the maximum energy and not the GZK effect. And what I meant by there's always some GZK effect, that's how you get the neutrinos, right? Because otherwise you'll get no neutrinos. And those neutrinos are the lower ones. So if you keep going down on that gray area, you keep having heavier and heavier components. So that makes it less neutrino production.
For the balloon experiment, was the reason for going to New Zealand just to get a super pressure balloon, or was there another reason for New Zealand?
New Zealand is super pressure balloon. We can be anywhere, but we love New Zealand. It's a beautiful place to go anyway. At least my husband thinks so.
You wouldn't want to do Antarctica.
And we love the easy life in New Zealand by comparison. I see some people who love to go to the South Pole back there, and over here too. And also the ocean for us is really nice, right? So if we have a lot of ocean, we have less light in general. But Anita, for example, needs the ice because that's their detector. We want the atmosphere. So as long as there's atmosphere and not too much light pollution, we're happy. So, but we could do Antarctica if we have to, yeah. But it would be nice to go back to New Zealand.
Does the alignment with supergalactic coordinates tell you anything about the source or what kinds of things it might be?
I think it will tell us something about magnetic fields and accretion onto that, big pancake. It's a very amorphous pancake, right? It's not like our galaxy, but I don't think it will tell us too much about the source. But that's my guess. We haven't explained it, so. Good questions. Keep them coming. Yeah. Polarization of. Yeah, I think the polarization guys are back in the room there for the CMB. So I think we are not that. Is this me? No, that's somebody up there. Yeah. I think we are not doing anything with polarization that we can think of yet.